We've had yet another Kansas quake, 2.7 magnitude, on the Mid-Continental Rift area near the border of Nebraska. And a lot of people don't mention Mid-Continental Rift. Unfortunately, it's there. It's found dipping from Lake Superior, the Great Lakes, and it's dipping towards the Dakotas, Nebraska, Kansas, Oklahoma, towards Texas, really in the central United States. And the geologists have ascertained that there is magma underneath. There's a hot spot, a mantle plume, and they don't know where it's coming from. Now, I wouldn't be surprised if you sort of extrapolate that line going down. You have in the Gulf of Mexico and near there, a number of volcanoes. They found asphalt volcanoes around the area of coastal Louisiana, Florida, and we even have a Mississippi volcano. We also have volcanoes in Kansas, the kimberlite diamond spitting volcanoes, basically in the area of this earthquake. Now, what is this mid-continental ridge that people don't know too much about? Well, according to the geologists, the mid-continental rift has characteristics of large igneous province, and it caused geologists to rethink some long-standing assumptions about how this giant feature was formed. Some of the Midwest's most scenic vistas are the black volcanic cliffs that tower over the blue waters of Lake Superior, the north shore of Lake Superior, and we've had various quakes there recently in Canada and the United States, north of Lake Superior and around it, and around the Great Lakes. And most people say, well, how is that possible? Well, it's because we have magma under there. Now, these have formed more than 1 billion years ago, and it illustrates one of the plate tectonic's most important processes, how continents form and also break up. And over geologic time, continents collide and fuse back together, and they also split apart again along these rifts. And rifts are linear features along which continents stretch, and when a rift succeeds, the continents split up. And when a new ocean basin forms between the two parts of the continent, that's how it happens. Some rifts, however, fail to develop into a seafloor, such as the New Madrid seismic zone and the Real Foot Rift zone. It should be called New Madrid Rift Zone because it's a failed rift. It never split totally. Maybe sometime in the future, millions of years from now, it will be it would have cracked, allowing the ocean to come in. Similar to that is the African Great Rift Valley. And at one point in time, that eastern part of Africa will be cut off, split off, allowing the ocean to flood into that area, into that crack. Now, so some rifts fail to develop into seafloor spreading centers and instead leave major relic structures with continents, fossils preserving the geologic environments that they form. The cliffs on the shore of Lake Superior and the lake itself are part of such a fossilized ancient rift. It's called the Mid-Continental Rift, MCR for short. It's 3,000 kilometers long, made of 1.1 billion year old igneous and sedimentary rocks, and it extends underground across the central United States. This is what is causing all these earthquakes in the central United States. It stands as one of the best examples of a failed rift, but it's still a puzzle. The Mid-Continental Rift's igneous rock shows us that there have been magma pools, far more vast than what one would expect in a failed rift, magma pools. So why was the Mid-Continental Rift so magma-rich? And scientists are now beginning to search for answers. Formation of the plate boundary, a traditional view of the formation and evolution of the Mid-Continental Rift involves two theories. First, the Mid-Continental Rift formed within the Laurentia area, the core of North America that is, that assembled in the Precambrian era. And the second is that the Mid-Continental Rift failed to split the continent because compression from a mountain building episode ended the extension, and also volcanism. The mountain building, called the Greenville orogeny, finished about 1 billion years ago, 980 million years ago. It was associated with the assembly of Laurentia and other continental blocks into the supercontinent of Rodinia. But the new view of this mid-continental rift comes from studies by the National Science Foundation's EarthScope program. One of this program's goals was to integrate geology and geophysical data so they could understand the growth and modification of North America over a billion-year timescale. And the new view begins from reanalyzing of the gravity data, showing that mid-continental rift extends farther south than they once thought. So it goes all the way down to Texas. The east arm had been assumed to end in Michigan at the Greenville front, the westernmost deformation associated with the Greenville orogeny. But this arm now appears to extend along the previously enigmatic East Continental Gravity High, which now seems to be part of the Mid-Continental Rift. The Greenville front goes above Lake Erie, basically a lake along Lake Michigan, towards the Laurentian Mountains of Quebec. So the gravity data showing that the east arm assumed to end in Michigan at the Greenville front, and the westmost deformation associated with the Greenville orogeny, but the arm now appears to extend along previously enigmatic East Continental Gravity High, now seems to be part of this Mid-Continental Rift. The arm stops at what scientists believe to be a fossil continental margin, where the Amazonia craton of Latin America, Precambrian rock found in northeastern South America, rifted from Laurentia. Amazonia rifted from Laurentia, from Quebec, what's now Quebec. So the Mid-Continental Rift probably formed during this rifting, and it failed because the seafloor spreading between the major plates was established. In this view, the Mid-Continental Rift's arm were boundaries of microplate with a plate boundary, similar to the arms of today's East Africa Rift. That's basically the same kind of a thing here, where the microplates exist in the zone where Africa is splitting into two major plates. Now, once seafloor spreading between the major plates is established in the East Africa Rift, some of the microplate boundaries should stop spreading and remain within the continents as failed rifts. The Mid-Continental Rift here of North America formed in a similar way as Laurentia and Amazonia split apart, and the paleomagnetic studies show that Laurentia's motion changed dramatically when the Mid-Continental Rift formed as volcanic rocks cooled. Magnetic minerals aligned with Earth's magnetic field recorded changes in the plate's motion. Such changes are often found in the paleomagnetic record when continents rift apart. And as part of the rifting, the Mid-Continental Rift formed and began extending. The region between the Mid-Continental Rift's two spreading arms was forced to move away from the rest of Laurentia as a microplate. But this is a hybrid rift. Dense volcanic material fills this area of central United States, the Mid-Continental Rift. Volcanic material. Concentrated mass exerts a greater gravitational pull than the areas around it, resulting in what's known as a positive gravity anomaly. In contrast, typical continental rifts have negative anomalies because they are filled primarily with low-density sedimentary rock. Tracing the gravity anomaly shows that Mid-Continental Rift's arms have characteristic geometric of rifts, linear depressions that formed as plates pulled apart and that filled with sediments and igneous rocks, and the depressions often evolved into plate boundaries. Calculating the volume of volcanic rock causing the positive gravity anomaly reveals something interesting. It's also a large igneous province, LIP, a region of extensive volcanism associated with upwelling and melting of deep mantle materials. MCR, Mid-Continental Rift volcanics, are significantly thicker than those at other large igneous provinces, LIPs, because magma was deposited within a narrow rift rather than across a broad surface. And therefore, the Mid-Continental Rift is a hybrid with the geometry of rift but the igneous rock volume of large igneous provinces. Now, how did this hybrid evolve? Reflecting from seismic data across Lake Superior shows how this unusual combination evolved. The Mid-Continental Rift is a basin between dipping faults that contains volcanic rocks up to 20 kilometers thick, overlain by about 5 to 8 kilometers of sedimentary rock. The lower volcanic layers truncate towards the basin's north side, indicating that they were deposited while the rift was extending by motion on the northern fault. The upper volcanic layers and overlaying sedimentary rocks dip from both sides and thicken towards the basin's center. They indicate that they were deposited after extension ended as the basin continued to subside. Radiometric dating shows that the volcanic rocks are about 1.1 billion years old. Another seismic line to the east shows a similar sequence but with extension on the southern fault. Basins produced by extension on only one side are called rift grabens. So the Mid-Continental Rift is a sequence of alternating half-grabens similar to what's found today along the arms of the Eastern African Rift. Working backwards from geometry of volcanic and sedimentary rock layers seen today provides the evolutionary model of this figure. The Mid-Continental Rift began as a half-graben filled by flood basalts. After rifting and extension stopped, we're talking about rifting and extension between Yellowstone volcano of Wyoming and Lake Superior region. All that area there is, as you can know, most of it is flat. This is actually the Mid-Continental Rift area. That's where we're getting all these earthquakes, all the way down to Texas. So after the rifting stopped, the basin further subsided, accommodating more flood basalts. After volcanism ended, subsidence continued, accompanied by sedimentation. The crust depressed and flexed under the load of the basalt and sedimentary rocks. It flexed and depressed. Long after subsidence ended, the area was compressed, process called basin inversion, which reversed motion on the faults and activated new ones. The original crust thinned during rifting as the crust stretched, re-thickened during the post-rift phase because of the added volcanics and sediments, and thickened further because of the compression when the basin inverted. If the model is correct, then crustal thickness along the Mid-Continental Rift should vary with the amounts of extension and volcanism and the amounts and direction of compression applied to that portion of the Mid-Continental Rift. But we also have surprises from seismic imaging, new insights on the Mid-Continental Rift from data from EarthScope seismometers and transportable array that rolled across the United States, the Superior Province Rifting EarthScope Experiments, free for short, flexible array, and the Canadian seismic stations. Seismic models covering much of the rift are being developed with this data. From the Lake Superior data, crust in the Mid-Continental Rift's west arm, that's what's coming down, the Mid-Continental Rift is like a horseshoe shaped, so the west arm comes down towards the Dakotas, Nebraska, Kansas, Oklahoma, Texas. So the west arm is thicker than its surroundings and is composed of sedimentary rock underlain by layered volcanic rocks. So if you combine the results with gravity and seismic reflection data, gives use of the Mid-Continental Rift's crust thickness and structure that will better constrain models of its evolution. The studies have already yielded surprising results. The Mid-Continental Rift's dense volcanic rocks appear clearly on gravity seismic reflection and receiver function data. The rift sedimentary rocks through which seismic waves travel slowly but does not see high velocity in the rift-filling volcanoes. The basalt rift fill is presumably denser than the surrounding crust, but the velocities of shear waves traveling through it are similar or slightly lower than those of surrounding rocks. Another surprise is that the formation of the Mid-Continental Rift left little signature in the upper mantle. Even though vast quantities of melt were extracted to fill the rift, the mantle shows no significant seismic velocity anomalies. Unless the mantle beneath the Mid-Continental Rift was replaced by a Mid-Continental Rift after the Mid-Continental Rift formed, melt depletion seems to have little effect on seismic velocity. The idea that extracting melt from the mantle would not change the mantle's seismic velocity significantly is surprising. Also, the mantle flows or oriented magma bodies usually make seismic wave speeds vary depending on the direction of the wave's travel, so waves tend to go faster along currently extending rifts than across them. But Ola and company and researchers in 2016 found that no such anisotropy below the Mid-Continental Rift took place, perhaps because much of the volcanism occurred after the extension ended. Now, did a hotspot supply the excess magma? The Mid-Continental Rift is an extraordinary feature that came from an unusual combination of continental rift and LIP, illustrating that over 1 billion years of Earth history, even unlike events can happen. Rifting can be classified in two types: passive rifting, in which forces pull the lithosphere in opposite directions, extending it, and also active rifting, where a mantle plume or hotspot thermally uplifts and stretches the crust above. For the Mid-Continental Rift, we suspect that the rifting continent by chance overrode a plume or a region of an anomalously hot upper mantle. So both active and passing rifting may have been at play here. Moosh and researchers in 2013 in their model implied that the Mid-Continental Rift's magma volume cannot have been generated by passive upwelling beneath an extended rift, even though Precambrian mantle was hotter than today's. And Bowles, Martinez, and Schultz in 2015 find highly conductive anomaly. They have found a conductive anomaly below western Lake Superior and northwest Wisconsin, extending to depths below 200 kilometers. That may have been formed by a mantle plume and somehow persisted. A question currently being discussed by geologists involves how the magma source operated over a long period of rapid plate motion. And of course, this is a rift failure. The Mid-Continental Rift was previously thought to have failed and stopped extending because of regional compression associated with the Greenville orogeny. But New Age dating shows that most of the compression recorded by reverse faulting occurred long after the extension and volcanism ended. So the rifting took place after the extension and volcanism. Thus, the Mid-Continental Rift's failure was not due to Greenville compression. Instead, it stopped spreading much earlier once seafloor spreading between Amazonia and Laurentia was fully established. Now, Mid-Continental Ridge Legacy showcase geology effect on culture. The MCR highlights geoheritage geology role in an area's culture and growth. Lake Superior is the surrounding spectacular scenery, national, state, and provincial parks. It's beautiful. The lake lies above the rift because soft sediment rocks within the MCR were easier for Ice Age glaciers to erode than the volcanic rocks. So the rift provided the region's first transportational system. Native Americans and Europeans used the lake to import and export trade goods. The lake remains an economic engine and tourist attraction even today. Also, the Mid-Continental Ridge mineral deposit shaped the region's settlement and growth. Water flowing through the volcanic rocks dissolved copper and deposited it in concentrations that became sources of valuable ore in many places around Lake Superior. For at least the past, you won't believe it, 7,000 years. For the past 7,000 years, Native Americans have mined copper and traded it as far as Illinois. The discovery of commercially viable copper deposits during the 1840s led to a mining boom that shaped the area's economy. Now, the Mid-Continental Rift is a place where visitors can interact with geological features that are over 1 billion years old. From extensional beginnings to rift failure, from Ice Age glaciers scouring it to lake infill, from ancient copper miners to modern boaters enjoying beautiful lazy summer days. Shows how geology weaves fabric not only of our continents but also of our lives. This was by the National Science Foundation, EAR, and I'll leave a link below for you for this. It's just a background on what is taking place today in this area. As you can see, the west arm, the east arm basically is parallel to the New Madrid seismic zone. And as we said before, the geologists are not sure where this mantle plume is coming from. Extended mantle plume is red, as you can see, Mid-Continental Rift. I wouldn't be surprised if it's coming from the Caribbean. There's a lot of activities and plates there. I would not be surprised if it's coming from there. Just like, for example, the Baja plume is supplying the western United States and even all the way up to Yellowstone. So we don't know yet. There are still a lot of things that geologists have to find out. So this is where we've had today's quakes and the swarms there at Kansas, Nebraska, Oklahoma, Texas. There's obviously activity there. That's where we have earthquakes, and we do have volcanoes there as well. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.